In this video, we'll talk about finding volume using cross-sectional slices. So here's a picture of somewhat of like what you're doing. This is a project that someone probably did in school. So a lot of times you'll be asked to find the volume using cross sections that are either semicircles, equilateral triangles, or squares. Those are very common. So here's one that looks like it was done with squares. Here's one that looks like it was done with semicircles. And here's one that looks like it was done with equilateral triangles. So you can just kind of see what it looks like in a 3D shape, because that's what you're doing, even though it doesn't seem like it because you're just doing calculus. Okay, let's do a problem. We're only going to do the integral. We're not going to actually find the area. Just set it up so you can see how to do that. So write the integral that represents the volume of the solid formed by using cross sections in the shape of a square, in this case, perpendicular to the x-axis, created by the region bounded by y equals the natural log of x, y equals e to the negative x power, and the line x equals 3. So let's draw a picture. That's always the first thing to do. So y equals the natural log of x is the red one, e to the negative x power is the blue one, x equals 3, and here's our bounded region. Here's the point of intersection that keeps them together. So we're talking squares that are perpendicular to the x-axis. So if you can just picture these vertical lines that I just drew, they're nice and perfectly straight. Picture that that is one side of a square, and then the other three sides are coming out towards you. Like here and here, pretend that there's two vertical lines pointing directly at you, and then connect them with another vertical line. So two lines shooting out towards you from the computer screen, and then you're going to connect them with another vertical line. So that's the square that you're creating. So this distance, these pink lines that I drew, represents the side of a square. And when you integrate a cross-section situation, the volume is the integral of the area. It just depends on what shape you're given. In this case, it's a square. So the area of a square is s squared, side times side. And I just said that this distance right here is one side of a square. And notice that that distance is the area between the natural log of x curve and the e to the negative x power curve. So it's area between curves again. And this represents the side of a square. And you're going to just need to find the area between, or I'm sorry, the distance between them, and then plug it into this formula because we're dealing with a square this time. Okay, so the side of a square is the area between those two curves. We have our top curve minus our bottom curve. Top curve is the natural log of x. Bottom curve is e to the negative x power. We're doing things perpendicular to the x-axis, so we're going to be integrating with respect to x. So we're talking about vertical distances here. So top minus bottom, you end up with natural log of x minus e to the negative x power. And that's it. That's your side. This is the side, and we're going to have to square it. And because we're going this way we're doing things with respect to x, we're dealing with 1.31, and x equals 3 is our limits. That's it. Of course, to integrate this, you would either use your calculator. I'd guess this would be a calculator problem because otherwise you'd have to FOIL this, and then I don't think you'd be able to integrate it by hand. But directions just asked to write the integral, so we just had to set it up. Done with this one. Let's do the same problem. Let's do an equilateral triangle this time. So it's literally the same equation, same boundary. Cross sections are perpendicular to the x-axis again. So same thing. If it was perpendicular to the y-axis, we would do everything the same. The formulas are all the same. It's just that we would be going horizontally again, and we'd be solving for x. So we don't have to do that in this case. But now, again, this distance from here to here, that's going to be the side of an equilateral triangle. That's one side of a triangle. So now picture at this point and at this point, they are shooting out towards you, but it's creating a triangle, so they're touching. It's not a square this time, it's a triangle, so they come out to a point. So again, when you're dealing with cross sections, the volume using cross sections is always the integral of the area of whatever shape you're dealing with. In this case, the area of an equilateral triangle is the square root of 3/4 times the side squared. That's not something that you might know off the top of your head, but if you're an AP student, you need to memorize that. And the side is the distance between those curves again. So the side of the triangle is the area between the curves. The area between the curves, again, is the top minus the bottom. Natural log of x is the top, and e to the negative x is the bottom. This is really similar to the square, almost the same problem, except now we just have a coefficient in the front. Oh, sorry. I didn't finish it. And we could put that coefficient out front here. Natural log of x minus e to the negative x squared with respect to x. Okay, last one. Now this is the one that people make the most mistakes on. This is the semicircle one. Same idea, same problem again, same graphs. Let me draw that picture again. And now we're dealing with a semicircle, so you know the volume is the integral of the area, whatever we're dealing with. In this case, a semicircle is half of pi r squared over 2. So we really can pull that pi over 2 out, and we'll have same limits, 1.31 and 3 again, because we're dealing with this section here. But now the radius is where things get tricky, because this distance right here between the curves, that's technically the diameter. Remember that picture at the beginning? The picture was, this is the diameter, and then picture a semicircle being drawn from it. That's supposed to be a 3D. So the area between the curves is the diameter of the semicircle. So in order to get the radius, you have to cut that in half. So we have, this is our diameter. The radius will be half of that area, which would be 1/2 times the natural log of x minus e to the negative x power. So if the distance between the curves is the diameter, and that represents this piece here, the radius is 1/2 of that. Now that 1/2, oops, that 1/2 is going to go right here. 1/2 of this thing, and we're going to have to square it. So be real careful. So we have the pi over 2, this 1/2 pi, this came out. This is right here. The radius squared, it's this thing squared. That's what's right here. 1/2 times the distance between the two curves squared. So be careful now, because when you have, this is 1/2 times something, and you have it all being squared, you're allowed to square them separately. The multiplication allows that. Here's why, just in a sidebar, totally separate example, just because of the multiplication, you're allowed to do that. Let's just say you have 10 and you square it. Well, that's 100. That's the same as doing 5 times 2 and squaring it, or 25 times 4. If you square them separately and then multiply them, that's why you're allowed to do this. So that was just a total sidebar. Ignore that example. But the most common mistake here is forgetting to square this piece right here. That's going to be a 1/4. 1/4, and then this piece, let's not square that piece because that's a mess. We don't have to actually find the area here. We can just leave it. But that 1/4 comes out, and it's technically 1/8 on the outside. And that would be your final answer.